So how is this related to 3D circuits? Well, one interesting thing about cells in the matrix is that they're somewhat agnostic to their connection topology. The behavior of an individual cell is purely a function of its internal lookup table and the inputs it's receiving from its neighbors. And it really makes no difference if those neighbors are sitting on the same two-dimensional plane, or if they're coming in from three different dimensions, or even if they're laid out in a single one-dimensional line of cells, each cell having two sides in that case. The number of sides on a cell is a function of the architecture of the cell, and that's fixed, that's hardwired. But the way that a cell processes its inputs, that's exactly the same no matter how it's connected to its neighbors. So the interconnection scheme and the topology and the dimensionality of the entire matrix really is no concern of the individual cells. Any global awareness of that needs to be sort of an emergent property of the individual awareness of the local situations. And this was one of the design principles of the cell matrix, was there was no centralized global point of view. Everything that comes out needs to be emergent from these local perspectives. So what's the connection to 3D circuitry? Well, we really like 3D circuitry for a number of reasons. One, you can build much denser circuits in 3D because your routing is a lot easier. If you're trying to build a circuit on a flat two-dimensional plane, routing can be very difficult. If you have even just a few layers, your routing gets a lot easier. And if you have essentially an unlimited number of layers, if you have a full 3D matrix where you have maybe 1,000,000 layers in your z-axis, it's very, very easy to build circuits without worrying about how wires are going to cross. And this is particularly attractive when you're looking at a system that's supposed to be building its own circuits or making changes to its own circuits. It just simplifies the routing tremendously to have this third dimension available. The other thing is you get a much tighter packing of cells. A two-dimensional array of a trillion cells is going to be a trillion cells on a side. A three-dimensional cube of a trillion cells will be 100,000,000 cells on a side, much more manageable. Lower propagation delays, sort of easier to imagine, if you will. So we like building 3D circuits on the matrix. It's very well suited for building 3D, and it maps into a three-dimensional realm just as easily as a two-dimensional. Now you can also go higher dimensional. You could come up with a connectivity topology that implements four-dimensional connections among cells, but that's not scalable. You have to sort of fake that by making different connections depending on where these things sit in the fourth dimension. And when you try to scale that out, you need to change the parts of your system that you've already manufactured. So your scalability breaks down beyond 3D. But at 3D, you can still scale a system. You can take two cubes, connect them together, and you get a big 3D rectangle parallelepiped version of a cell matrix. So it's really intended to be working with three-dimensional circuits, just because that works a lot easier for us, and it gives us a much better cell count per area.